different kinds of letters.
Okay, guys, so let's start. Today's talk will be given by Marc Serra Peralta. He got his degrees in physics and chemistry in Universidad Autónoma de Barcelona in Spain. And he's now doing the quantum track in the Master of Applied Physics here in TU Delft. Well, Marc's interests are very wide. He has worked on, for example, simulation of water formation in interstellar grains, and also, for example, in big data analysis of music harmony. But right now, he's very much interested in quantum applications. So, for example, quantum algorithms for example, in NISQ era or in the fault-tolerant era. So, today's paper was written about Johnson now. Well, sorry for the pronunciation, but Josie Chen and Neil Pisenti. They all work in IonQ, which is a quantum computing company that uses trapped ions, and it was founded by Jung-San Kim and Christopher Monroe. And so, yeah, these founders also contributed to the paper. And so, without further ado, please, Marc.
Thanks, Danny. Today I will be presenting the paper Ground State Energy Estimation of the Water Molecule on a Trapped Ion Quantum Computer. In this article, the authors present a smart way of implementing an algorithm known as Variational Quantum Eigensolver to estimate the ground state energies of molecules using this type of quantum computers. Before we start to go deep, why are ground state energies important? Well, in order to know if a reaction takes place, this means going from the reactants to the products, we check if the variation of the Gibbs energy is negative. And this variation is related to the difference between the ground state energies of the reactants and the products. With this energy difference, we can also determine how much product we will produce in equilibrium or how fast we will be able to produce it. The method of excellence to estimate these ground energies is the variational method, and we will see how it is applied to our problem of chemistry, as well as its quantum version, the variational quantum eigensolver. Then I will summarize the main ideas and characteristics of the paper so that we know what we are dealing with in the next two sections. The crucial step of variational method is choosing a good trial wave function to represent the ground state, and this will be one of the main blocks of the presentation. Then I will summarize the main results that the authors obtained in the paper, and finally we will end obviously with some conclusions. The variational methods are based on the variational principle or theorem, which states that the average energy of any wave function is always greater or equal than the true ground state energy of the system. What the variational method does is say, okay, I have a trial wave function that depends on some free parameters for the ground state. Then I calculate the average value, the average energy of this wave function, and if I minimize it as a function of the free parameters, I can get it lower, lower, and lower until it's very close to the true ground state of the energy of the system. So in conclusion, we get a good estimate of this true ground state energy. This minimization step is actually done in an iterative way. So we first start with our trial wave function and with some parameters, calculate the average value of the energy as well as its gradient with respect of the free parameters, and update these parameters towards the minimum of energy. And if we repeat this again and again and again, we will find this minimum of energy. There are two ways of choosing the trial wave function. In the first one, it's done using some functions that have some intrinsic parameters inside. You can think, for example, of a Gaussian, where you have the mean that you can vary or the standard deviation. And in this case, those are the parameters that we optimize. In the second option, the trial wave function is a linear combination of fixed functions. The free parameters are now the coefficients of the fixed functions, in this case C1 and C2. For the special case of this second option is that if you have a problem which is similar to a less complex problem that you can solve analytically, you can use the eigenfunctions of this problem as the starting points for your fixed functions. as in chemistry we can solve the hydrogen atom, we use this second option. So therefore, our trivial wave function is a linear combination of the atomic orbitals of each atom. The next step is minimizing the average energy with respect of these coefficients so that we get an estimate of the true ground state energy of the system. Then the trivial wave function is a linear combination of the spinel orbitals. They are known like this because they depend on both the position of the electron and the spin of the electron. The main problem with this method is that you need lots of coefficients in order to have a good trivial wave function and therefore a good estimate of your true ground energy. In some cases, the number of coefficients is too large that you cannot fit them inside the memory of a classical computer. And this is the reason why we use the quantum version, the variational quantum eigensolver. As you can see, we start with the same steps as the classical algorithm, but now we encode the trivial wave function inside the qubits of a quantum circuit. For n qubits, we can store up to 2 to the power of n coefficients, so it grows exponentially, solving the problem that we had in the classical version. The minimization step now goes like this. So we start with our qubits in the state 0. We apply some unitary transformation which depends on our free parameters in order to put the qubits in a state that represents our trivial wave function. Then we measure all the qubits and calculate this average value of the measurements, which we can relate to the average value of the energy. With that, we can update the new parameters towards the minimum, and we repeat this again and again and again and again. Now that we know how and why to apply the variational quantum eigensolver, let's take a look of what they have actually done in the paper. The main claim of the authors is the design of a smart procedure for obtaining the ground state energies of molecules using the variational quantum eigensolver, which is specific for trapped ion quantum computers. The smart part is because they have reduced the total number of gates needed to implement the trivial wave function into the qubits, and therefore they have reduced the implementation error. To show that it actually works, they have applied to estimate the ground state energy of the water molecule. The general first step of the variational quantum eigensolver is to start with the most common variational method in classical computational chemistry, which is the Hartree-Fock method. It has two main advantages. It ensures that the wave function is antisymmetric and it is computationally fast. This is because it uses a mean field approximation for the electron-electron Coulomb interaction during the optimization of the free parameters. In particular, an electron interacts with a density of electrons instead of each electron as a pair. The disadvantage of using this mean field approximation is that the results are not very good, so we use another method that gives more precise ground states estimates, which is the post-Hartree-Fock method. The key idea of this method is to start from the spin orbitals of the Hartree-Fock and then include some kind of excitations. I know it sounds a little bit counterintuitive to include excitations when we are trying to find the ground state energy of the molecule, but we will see how this works with an example. Imagine that you have two electrons, 1 and 2, which are very close together but very far away from all the other electrons. And we can put them in level A or level B. In the Hartree-Fock method, the algorithm will go something like this. Okay, I have electron 1, which interacts with this mean field approximation, in this case the electron density, which is very far away from it. So I can put it in the ground state energy, as you can see here. And the same reasoning for the electron 2, in this case. If we calculate now the exact energy, this means without including the mean field approximation, the electron-electron Coulomb interaction will be very high because the electrons are very close together and their wave functions overlap a lot. In post-Hartree-Fock method, we can include some kind of excitations. In this case, we excite the second electron to level B. Now, the exact energy will be a little bit higher due to this excitation, but the potential interaction will be way lower, because although the electrons are still very close together, the overlap of the wave function is now way lower. So now that we know how the post-Hartree-Fock methods work, let's check the smart procedure that the authors have chosen to implement the trial wave function into the qubits. It has three main ingredients. The first one is the coupled clustered method. This is a post-Hartree-Fock method because, as you can see here, we start from the spin orbitals of the Hartree-Fock, and then we apply some transformation which depends on the excitations of the electrons. In particular, this T is a linear combination of our free parameters and all the excitations of the electrons. We can approximate this as a product of single pair excitations. The second ingredient are the XX gates, which are given by this formula. And as you can see, this is very close to the single pair excitation. The last ingredient is knowing that the XX gates are native in trapped ion quantum computers, and therefore we can implement them very easily without having to decompose them in other unitary gates. So using all these ingredients, the the single pair excitations is implemented using this circuit, which is way shorter than the general one that we use for this kind of excitations. So in conclusion, we can reduce the total amount of gates needed to implement our trial wave function into the qubits. The downside of this method is that it doesn't actually work for all kinds of excitations. Only for the bosonic ones we can use this smaller version, and for the fermionic ones we still need to use this longer version. However, we still reduce the total amount of gates. So now let's apply this to our case of a study, which is the water molecule. The water molecule can have up to 5 bosonic excitations, which we will need a maximum of 5 qubits and 10 XX gates. If we want to include the fermionic excitations, then the number of gates grow very fast because we have to use the longer version, up to 178 XX gates. The authors have experimentally implemented the bosonic excitations, as you can see here, and they have numerically simulated the algorithm, including the bosonic and the fermionic ones, which are all the other points. As you can see, if we include more excitations, this is going to the right, we can lower our average value of the energy and having an estimation which is very close to the true ground state energy of the water molecule. In particular, we don't have to include all the fermionic excitations because, as you can see here, it doesn't actually get closer to the true ground state. But still, with the bosonic excitations, it's not enough to have a good estimate because it is very far from the true ground state, so we need to include some fermionic ones. But still, the total number of gates is not that high. So, in conclusion, we have seen how to apply the variational quantum eigensolver to a problem of chemistry, which is the estimation of the ground state energy. And we have also seen some tricks in order to reduce the number of gates needed to implement the trial wave function into the qubits. If we apply these tricks to the water molecule, we have seen that we can achieve a very good result for the ground state energy. The overall conclusion is that the authors optimized the variational quantum eigensolver circuit using some hardware-specific advantages, which in this case, they have used the fact that the XX gates are native in trapped ion quantum computers, and therefore they are very easily to implement. And that's it. Thanks for your attention. Before going to the discussion, I have a small example / demo that I want to show you. The Penguin library, and what they have implemented is they have used the variational quantum eigensolver for the case of the hydrogen molecule, as you can see here. The first step they do, which I haven't actually explained in the presentation, is to express the electronic Hamiltonian as a linear combination of measurements that we can do in our qubits. If you remember, one of the steps of the iteration method was to relate the average value of the measurements with the average value of the energy. And for that, we need this linear combination of measurements. For this, we need first the second quantization, because the electronic Hamiltonian is a function of, well, is expressed for the wave function, so you have some Laplacians there, x, y, z coordinates, which we cannot actually measure in the qubits. So we do the second quantization to express the Hamiltonian as the annihilation and creation operators, but still we cannot measure these operators in the qubits. So we use the Jordan-Wigner transformation, which relates these annihilation and creation operators to Pauli matrices. So our Hamiltonian is a linear combination of Pauli matrices, as you can see here, for example, the Z to qubit 3 or the identity to qubit 0. Okay, this one is actually small. For the case of the water molecule, the Hamiltonian is way longer. Yeah, I mean, maybe we don't have to include all these terms because some of them have like very low contributions, but still it's quite long. Okay, the next step is the actual implementation to a hardware backend. Here they select the one that they want to use. And as you can see here, they also use this post-Hartree-Fock method with these double excitations. You have two electrons that you excite. Here they use the G matrix, the G rotations. In our case, they use the XX matrices. And these G are known as these Gibbons rotations. Okay. Also, for the post-Hartree-Fock, the other part was the spin orbitals of the Hartree-Fock. This is done in this variable. It's just putting all the electrons in the ground state of the spin orbitals. That's it. So our circuit is just initializing this state and then adding all the double excitations. For the optimization procedure, we need some cost function, which our case is just the average value of the energy because we want to minimize that. So the cost function is just the expectation value of the Hamiltonian. Then we select a classical optimizer, which in this case is the gradient descent, and some initial values for our free parameters, which in our case they chose 0 because they wanted to start from the Hartree-Fock state. With that, the only thing that we have to do is do all the iterations and update the free parameters, and then the average energy will just go lower until we hit this minimum that is here. So it goes lower until it gets very close to the true ground state of the hydrogen molecule, and that's it.